Hi, in this video I would like to discuss quantum numbers and where are the electrons as they're determined by those quantum numbers. So far in class we saw the first quantum number n, and that gives us the distance from the nucleus where we find an electron. So let's define that first quantum number. And that is n, and that gives us an idea of the distance from the nucleus where we find an electron. And this is a probability function. So it tells us we can find the electrons at a certain distance from the nucleus with a given probability. And n has numbers of whole numbers of equals 1, 2, 3, and so on and so forth, all up until infinity right here. And this really then tells us, in a probability basis, how far the electron is from the nucleus. So if we have here the nucleus with a positive charge of an atom, then we can say, for example, at n equals 1, some distance from the nucleus, we know that negative charges and positive charges repel each other, so the electron there'll be some attraction and repulsive forces right here from electrons and protons, so it'll be some distance from the nucleus. So let's say right here, this is the electron right here, and it is n equals, the distance right here is n equals 1. That is the distance from the nucleus. Then if we keep on going right here, n equals 2. So this would then be the distance n equals 2. And n equals 3 is going to be a little bit closer. And so on and so forth. And it starts to converge. So once we get to infinity, really infinity does not mean all the way at some infinite distance from the nucleus. It really converges at some upper limit. Once we get beyond that, we're effectively ejecting the electron from this atom right here, and a lot more energy is involved right here. So n equals 4. And so it gets tighter and tighter, and n equals 5 is over here, and so on and so forth. So it gets, it is not an infinite series, it converges. And then we end up with infinity somewhere over here. So it converges. So it is not infinite. So next we can find the second quantum number. So first principal quantum number n. The second one is then called L. That gives us an idea of the shape of the region of space where we find that electron. Again, as we saw in the reading, the electrons can be defined as being as part of a wave function, so we can describe that wave function as a region of space where we have a high probability of finding that electron. So L gives us an idea of the, so this would be the second quantum number right here. L gives us an idea of the shape of the region of space where we find the electron. And L can have the numbers of equals 0, 1, 2, and so on and so forth, all the way up to n minus 1. Again, as we saw before, n can have whole numbers right here. So n can have numbers 1, 2, 3. It cannot be 3.1415 or anything like that. Always whole numbers all the way up to infinity. And likewise with L, it has the same pattern right here all the way up to n minus 1. So if L, so it depends on n, and That is really worth noting. Let's note that right here. So it depends on n. And that's given by this relationship where that's all the way up to n minus 1. So let's do as an example here. If n equals 1, L can only be 0 because it has to be less than 1. So L can only be 0. And when L equals 0, it makes a spherical orbital. And so that's called an s orbital. And it's a spherical orbital. It looks just basically like a sphere. And here's an illustration of one. So it's just a sphere, and so that means that we can find those electrons in that sphere at some distance from the nucleus. And so a nice way to remember this, S stands for sphere. Now if n equals 2, then L can equal 0 and 1. So always n minus 1. L can equal 0 and 1. And this is now called a p orbital. This is called a p orbital, and the number p stands for principal. That's based on some principal line they saw on some kind of alkali metal spectrum, and that's where these names are based off. So they don't mean much of anything, but we can think about the shape of these is sort of a dumbbell or bow tie shaped. And let's move this to the next slide. So a p orbital would have a shape like this right here. So this is a picture I got from our book right here. So we can call this sort of a dumbbell, or some people would call it a bow tie, or maybe peanut shape. So it's basically two lobes on each side of the axis right here. So we end up with lobes in 3 directions right here. And so this is then called a p orbital. Some people like to also call it peanut, and that might be the easy way to remember it, the shape, because it is sort of like the 2 lobes of a peanut with the nuts inside. Okay, so we can think about it as that. That might be one way to remember it. So it's also called, so the real name is principal. So that might be hard to remember, so it's dumbbell or peanut shape. Now if we go to n equals 3, that means L can be 0, 1, and 2. Now we've already learned that L equals 0 is an s orbital, L equals 1 is a p orbital, and now L equals 3 we call a d orbital. It stands for diffuse. And these are sort of have a little bit of a funnier shape right here, and they have multiple solutions right here, so they can have sort of this double dragonfly kind of shape here. So we've got like 2 lobes on each side. They're equivalent of the between the xy and xz axis right here, or so they're all equivalent in other solutions that are a little bit more funny. So in general, we have, though, predominantly these kind of double dumbbell arrangements right here. So you can sort of draw it like, 1 lobe in one direction, another lobe in one direction, and then another lobe in one direction, another lobe in the other direction. And so it's kind of like a double dumbbell, or some people might call it a dragonfly, so you can remember what this looks like a double dragonfly, the wings of a dragonfly, so just so that you can remember it. And again, this stands for in reality, this stands for diffuse. The name stands for diffuse. Again, this is based on the spectrum lines, and so the words might not mean much right now. If n equals 4, then L can equal 0, 1, 2, and 3. Zero, 1, 2, and 3, and in this case again, 0 stands for an s orbital, 1 is a p orbital, 2 is a d, and now the third one right here, we call this an f orbital right here, and that stands for fundamental. And I don't really have a good abbreviation for it, so it's just an f orbital. It has the shape of sort of a double dragonfly in some cases. So these are the pictures from your book. So there's multiple solutions to those, and so we can think about this sort of a double, here are some of these sort of a double dragonfly, so two sort of 2d orbitals superimposed on each other. But then there's also some other solutions right here that are not a little bit more strange. So it's, again, these are again regions of probability where we find the electron. So there are not these circular planet models that we might have seen from some textbook in elementary or middle school. These are really then more advanced theories as to describe these electrons as some waves that are around the nucleus of an atom, and these waves are standing waves that produce different solutions based on the uncertainty principle. So we've got now these 4 principal quantum numbers. There's actually not many more right here, and we can then look one further right here. We can see the third quantum number is the third quantum number that we need to evaluate is the magnetic quantum number, and it's m sub L is the abbreviation for it. So now we've looked at N, L, and now we're looking at m sub L, that is the magnetic quantum number. And that one can have values of minus L through 0 through plus L. So if L equals 0, and that's what we saw that is in the case of an s orbital, then m sub L equals 0 as well. So that means that for this s orbital right here, again, this is an s orbital, we can really only have one of those available. So again, we look at these spheres right here, there's only one possible solution of this s orbital. So we only have one s orbital at this level. Only one s orbital at that level. If we go to L equals 1, L equals 1, then m sub L can equals then minus 1, 0, and plus 1. And so that means that there are 3 solutions to this orbital, and that's reflected then in the 3 p orbitals that we can see right here. So we have then 3 p orbitals, and so we have one orbital in the x-axis, one orbital in the x-axis, one in the y-axis, and one in the z-axis, and one in the y-axis. And that explains that we have then 3 p orbitals at this level. So it means we can have up to 3 p orbitals. If we then look at L equals 2, and that is now a d orbital right here. We then have m sub L equals minus 2, minus 1, 0, 1, and 2. So we basically have 1, 2, 3, 4, 5 possible solutions right here, and that is reflected now in 5 possible d orbitals that we can have. So we have 5 possible d orbitals right here at this level. So these are then, we have 5 d orbitals. And last, we get to the f orbitals, and then if we have L equals 2, L equals 3, then we have m sub L equals minus 3, and so on and so forth. M sub L equals then minus 3, minus 2, minus 1, 0, 1, 2, and 3. So we've got 7 possible solutions right here for this orbital right here, and that means that we then have 7 f orbitals. And so we have 7 f orbitals in the solution right here. The last number that we need to evaluate right here is the spin quantum number, and that is m sub s. And that is the spin quantum number. And that one can have values of plus 1/2 or minus 1/2. And what that means is that in one of these electron orbitals, there can be up to 2 electrons, each with opposite spin. So we can indicate the plus 1/2 with an up arrow and the minus 1/2 with a down arrow. So that means that each orbital can have up to 2 electrons. And when an orbital has 2 electrons, they both pair each other up with opposite spin. Each orbital can have 2 electrons with opposite spin. Okay, I think that is it for this video. Let's see another couple of practice problems, and we will get to actual electron configurations for an atom in another in class. Thanks for watching.